Programming languages face a persistent structural trade-off. Compiled languages convert code directly into machine instructions, offering raw speed, but they remain chained to the specific hardware they were compiled for. Interpreted languages read code on the fly, offering flexibility across systems, but paying a heavy tax in performance speed. Java resolves this friction through a multi-layered architectural pipeline. It physically separates the environment where a developer writes the software from the environment where the machine actually executes it. The first layer of this pipeline is the Java Development Kit, or JDK. This is the complete, self-contained toolset developers use to write and initially process their source code. This diagram illustrates the first phase of translation. When a developer runs the Java-C compiler, it scans the human-readable .java text file. It strips away that text entirely, outputting a densely packed matrix of instructions known as bytecode. This resulting bytecode matrix is not machine code. If you try to feed it directly to a computer's processor, it will fail. It is an intermediate instruction set, existing in a suspended state, waiting for a translator. The Java compiler does not target the computer's physical hardware. It targets a virtual machine. By doing this, it shifts the heavy engineering burden of system compatibility entirely away from the software developer. To wake that suspended bytecode up, the target machine needs the Java runtime environment. The JRE acts as the deployment container, supplying the necessary standard libraries and housing the execution engine. Inside that execution engine sits the Java virtual machine. This animated diagram shows three distinct hardware architectures: Windows, Mac, and Linux. The uniform JVM component drops directly into the center of all three, acting as the final translator in the pipeline. As streams of identical bytecode enter the JVM, a just-in-time translation process occurs. The JVM converts that universal bytecode into the highly specific, complex machine code required by the host operating system, executing it on the fly. This execution sequence can be influenced at launch through command line arguments. If a user runs the program by typing java demo sing, the JVM intercepts those external inputs and securely ingests them as an array of strings directly into the program's main method. A developer writes one file, and it runs anywhere. Platform independence is a meticulously engineered illusion, achieved by forcing a universal intermediate layer to absorb the chaotic reality of hardware translation. Once the execution engine is running, the bytecode requires strict structural constraints to organize its logic and data without collapsing under its own weight. This begins with the class. In Java, a class is a rigid, lifeless blueprint. It dictates exactly what properties and behaviors a data structure will possess, but it contains no actual data itself. Look at this wireframe outline of a student class. Because it is strictly a blueprint, it occupies zero footprint in the system's memory. It defines slots for a roll number and name, but remains empty. That changes the moment we use the new keyword, triggering instantiation. The transparent blueprint clones itself, solidifying into a tangible object, dropping directly into active system memory to hold real values. Classes dictate the theoretical architecture of the application, but objects are the physical, memory-consuming entities that the JVM actually manages and tracks during runtime. When thousands of these objects occupy memory simultaneously, they need to communicate. Uncontrolled data mutation during these interactions poses a fatal threat to system stability. Java mitigates this through abstraction. This code layout shows a simplified shape interface on the left, mandating an area calculation. On the right, the circle and rectangle classes use entirely different math formulas to achieve that calculation. Abstraction hides the internal complexity, demanding what must happen without dictating how it happens. To protect the actual data within those shapes, Java uses encapsulation. This defensive mechanism wraps data and restricts unauthorized outside code from accessing it directly. Developers execute this by declaring data variables as private and then providing public getter and setter methods. This pattern creates a tightly controlled, predictable gateway for any data modification. If a developer needs to eliminate the possibility of modification entirely, the compiler provides the final keyword as an absolute strict mode toggle. Applying final to a variable locks its value permanently. Applying it to a method prevents any child class from overriding that behavior. Applying it to an entire class stops that blueprint from ever being inherited. These object-oriented principles operate as strict compiler-enforced constraints. They are designed specifically to protect the application's internal state from rogue data manipulation. Real-world applications cannot survive by executing tasks sequentially. To handle heavy workloads like web traffic or data processing, a system requires concurrency. Java achieves this through multithreading. This visualization shows a single execution path forcefully dividing. The application spawns independent threads to handle parallel operations simultaneously. Look at these side-by-side code blocks. Developers can spawn threads in two distinct ways, by extending the thread class or by implementing the runnable interface. Implementing runnable is the architecturally superior design pattern. Java strictly enforces single inheritance. A class can only extend one parent. By using the runnable interface for threading, the sole inheritance path remains available for other essential system classes. Developers can assign a priority level to each thread, scaling from 1 to 10, to signal its importance to the JVM scheduler. However, the precise execution order ultimately remains at the mercy of the host operating system. Multithreading inherently introduces chaos. Java relies on rigid design patterns like runnable to maintain architectural flexibility while safely attempting parallel execution. The JVM operates as a pristine, closed environment, but applications must eventually connect to external, unpredictable resources, like local hard drives or remote databases. This introduces massive instability. When writing data to a hard drive, a raw FileWriter executes character by character, which is intensely slow. Wrapping that FileWriter inside a buffered writer provides a critical speed advantage by batching data in memory before executing the physical write to the disk. Because these external resources can fail, a file might be missing or a database connection might drop, Java enforces the use of checked exceptions, such as file not found exception and SQL exception. The JVM cannot control a severed network cable. Therefore, the compiler physically forces the developer to write explicit contingency logic. This breakdown of a JDBC database connection shows the driver loading sequence completely surrounded by a mandatory try-catch block. If the connection fails, the catch block intercepts the error and prevents the entire application from crashing. To handle simple single-method operations during these data exchanges without bloating the codebase, Java utilizes functional interfaces and lambda expressions. Notice how this verbose inner class compresses down into a single, elegant lambda expression, reducing architectural friction. From the invisible bedrock of bytecode inside the JVM, to the strict defensive layers of object-oriented programming, to the heavily guarded pathways of database queries, Java is an interconnected fortress designed to balance ultimate flexibility with absolute, uncompromising system resilience.